Hello guys, welcome back to Mason African Motives. Still working on our electrical trade theory N2. We shall have our revision of the question paper which was written in the April 2023 exams so that we can try to check as we are preparing for our exams which are ahead of time. So we're not going to waste much time. Let us quickly rush through the questions and see how we are given. Remember your instructions and information. Read them properly so that you understand each and every part that you are given. So like I said, without wasting much of our time, let us see how these questions were being given so that we can check how to attempt these typical for our exams. The first part, which was on our AC theory, we've got question number 1.1, which is indicate with the aid of a neat labeled circuit diagram. Take note, we need a circuit diagram. In this case, the stator windings of a motor connected in a star. So meaning to say, if it is connected in star, definitely we are talking about a three-phase system in this case, where it can be in star or it can be in a delta. So in a star connection, this is what we are going to have in this case, whereby what you need to indicate properly there, the major part is to show your lines, in this case, red, yellow, and the blue in this case. All right, so we've got red, yellow, blue in this case, which is from our terminal box, also the bridge places. And we can have this in an alternative way in this case, whereby we are having the start point here, the motor windings, this being our supply. So as we know that we have got the phase currents and the line currents, which are the line currents in this case from our three-phase supply in this case. And here we are now having the phase currents in this case, which is the same part on our supply. That is where we are having what? Our line currents. Then inside that is where we are having the phase currents in this case. So that is the major part also to be indicated on our diagram. All right, that was on the stator windings of a motor in a star connection. Then we've got 1.2, define each of the following terms. All right, we've got 1.21, whereby we are asked to define what is referred to as the form factor in this case. All right, so the form factor again is from our AC. This part whereby we are saying the form factor is defined as the ratio of the RMS value of a wave to its average value. That is what we refer to as what? As the form factor in this case. So in a condition that you have forgotten this part, what you need to refer is to refer back from your information sheet. We are already given these formulas. If we check, I want you to check something here on your formulas. We have formulas in our formula sheet, so you can refer to that part in case that you have forgotten, whereby we are already given that the form factor in this case is the RMS value over the average value. So you can define as it is the RMS value divided by the average value. From the formula, you can actually define it like that, the same as the crest factor in this case. All right, so that is when you are limited in exam, please do so to check on your formula sheet so that you can be assisted on how to define this part here. Then we move on to the other part on 1.22, whereby now we are asked to define or to give what is referred to as the power factor in this case. All right, so the power factor being taken from our power triangle, which is that the power factor is defined as the ratio of the true power to the apparent power. Remember the power factor, if we are to have our triangle in this way, all right, let's just say we've got our triangle in this case, which represents our power in terms of the power factor from the theta that we have there. So we are going to see that in this case, we are having our power, which is the true power in this case, which is taken from our apparent power, S, which is given as VI, that is voltage times current. Here we are now having the actual power, which is the true power, which is referred as VI, the cosine of theta. That is what we have on the power. Then here we are now having the reactive power, which is referred to as VI, the sine of theta. So this is what you need to understand. This one measured in watts or kilowatts, and this one measured in volt amperes. So this one is measured in volt amperes in this case. All right. So if we are to refer to the power factor now, which is the cosine of theta, we are simply saying, remember the cosine of theta, the idea that we have on the cosine of theta. We know that this is the ratio between, from our SOHCAHTOA concept. All right, this one is not, let me change to this. All right, so like I was saying, from our trigonometry, the ratio of cosine in this case is taken as the cosine of theta being adjacent over the hypotenuse in this case. And that is what we have on our diagram in this case, to say our cosine of theta is the adjacent, which is the true power in this case, that is the adjacent over the hypotenuse in this case, which is our apparent power. So that is the idea that we have. So if we are to simplify this, if you take this part here, VI cosine of theta, you divide to voltage times current. As you can see, we remain with the cosine of theta, which is the one that we are having here. That is the part they were asking in this case. So in this case, we're just giving a definition, just a definition, not to say you're supposed to draw the triangle and so forth. No, that one is just for us to see what is happening there. All right, on 1.3, we're given the information on a three-phase delta connected motor. All right, so we are in a three-phase, we are in a delta that draws a current, in this case, of 8 amps and 380 volts in this case. All right, so this is power, a supply of power factor 0.5 lagging. So let's take this. If the motor is drawing a current of, it's from the line current, this is the supply, it's drawing, that is the current taken. So it's taken from where? From the supply. So meaning to say there, you'll be talking of the line current in this case. All right, so we are given that this is a three-phase, all right, and also connected in a delta. All right, so that is the major part that we are given there, delta connected. So we have got the line current as we are given, which is the 8 amps, and we are also given the voltage from the supply of 380 volts. That is this, it draws a current from a 380 volt supply. So that's our line current, and having a power factor of 0.5, 0.85 lagging in this case. So we are given the power factor of 0.85 lagging in this case. All right, so remember we said the power factor simply represents the cosine of what? The cosine of theta. That is what represents the power factor. All right, we are given that it's in a delta connected. So like I said, if you forget any information, visit your formula sheet so that you understand what is it that we have under the three-phase dealing with the power. In this case, all right, this one is giving us about the power that we have in for three-phase, all right, the apparent power, the true power, the reactive power. But we also have the connection of these formulas in this case that are being in a delta or in a star. So this is the part that I want you to check here, so that you will not be limited under exam. If you check, we are given that in a star, these are the formulas that you're supposed to apply. In a delta, these are the formulas that we are supposed to apply. So meaning to say, as we are focusing with a delta connection, so we're going to be focusing with these formulas that we have here, whereby we are saying in a delta connection, VL must be equal to VP, that is the line voltage to the phase. IL is equal to the square root of IP, that is the line current to the phase current in this case. All right, so these are the formulas that we are going to consider as long we are dealing with a delta connection in this case. All right, so we saw that in a delta connection, the line voltage is equal to the phase voltage, but the line current is equal to the square root of 3 times the phase current in this case. And every power that you're going to take will be multiplied by the square root of 3. That is what we saw again. So We're not going to waste much time. Let us see what you're given here. First part of our question was the first angle at which the motor is operating. All right, the first angle. So the first angle is taken from where? Already we are given that here it is having a power factor of 0.85 lagging. So from the power factor that we have, we can find angle, because we said power factor represents the cosine of theta in this case. All right, so if the power factor is representing the cosine of theta, therefore we are simply saying the cosine of theta is equal to 0.85. So how do I find theta? So theta is going to be the arc cos of 0.85. That is arc cos. From our mathematics, we talked about arc cos of from our trigonometry there. So from our calculator, what we simply need is this, all right? That is arc cos, which is going to be shift cos, like this. That is arc cos, shift cos. Your calculator is now, your calculator must be in degrees always. So here we are now determining arc cos of the decimal that we are given, 0.85 in this case. So this is going to give us the angle in this case. That is going to be 31.788 to 3 decimal places. All right. So theta is going to be 31.788 in degrees in this case. So that's how we calculate our first angle, that is our theta, lagging from the concept that we are given in this case. All right, so that is it, guys. All right, then we are given in this case to calculate the apparent power in kilovolt amperes. Remember, I said the apparent power is measured in kilovolt amperes. So we are asked to calculate this apparent power. All right, we take note, we are in a three-phase system. We are working with a three-phase system, and everything that we are going to be working with is going to be multiplied by the square root of 3 in a three-phase system. Like I was saying, from our power triangle in this case, whatever that you are going to calculate this time will be multiplied by the square root of 3. But if you have forgotten this, like I said, visit your formula sheet, like I showed you these formulas that we are going to have when dealing with the power in this case. All right, so let me just show you this part, guys. I referred to these formulas, if you still remember. So these are the formulas that we are going to work with in calculating of power. S equal to square root of 3VL IL. Take note, we are working with line voltage, line current, line for every part. The power, square root of 3, wherever that you're going to have the reactive power, every part is going to be multiplied with the square root of 3. So that is the whole idea of this. All right, so there we are asked to calculate. First part was the apparent power. So apparent power is given by S. So meaning to say, we are going to have 1.32. S is equal to square root of 3 VL IL. That is line voltage and the line current in this case. And this must be measured in kilovolts. So you can just calculate your S in this case, which is square root of 3 times VL. We already have this, which is 380 times IL. We have this one, which is 8. So that means our S at the end is going to give us 5265,443, something like 434. But we are asked to leave this answer in kilovolt amperes. In this case, it's in volt amperes like this. So to convert now to the kilovolt amperes, what are you going to do? You're simply going to divide by 1000. So you're going to have your answer as S is equal to 5. So we are going to obtain at the end, this is going to be 5,265. All right, 5,265 in this case, that is in kilovolt amperes. So that is the idea there. Three-phase system. We are supposed to work with what? With the square root of 3. If it is a single phase, we are simply having voltage times what? Voltage times current. But because of the three-phase part, we are supposed to work with the line voltage, the line current, and also every part is being multiplied with the square root of 3. All right, so that was the idea of our question. Then if we move on to the other part, now we need the true power, as we saw that the true power, that will be in watts, but here they want this answer in kilowatts in this case. So how are we going to calculate our true power? That's the question. All right, so 1.33, remember, The true power is given as square root of 3 VLIL cosine of theta. But knowing that this cosine of theta represents our power factor, that's the power factor in this case. Remember, we say the power factor here, that's our cosine of theta. So we're simply substituting this part as it is before. So our power is going to be square root of 3 times all this part as it is 380 for our VL, IL, which is 8 times the cosine of theta now, which is our power factor. And our power factor, we have it, which is 0.85. So we're going to multiply these two 0.85. That is the whole idea there. So this is going to give us the true power in this case. So if you have to calculate this, you're going to obtain something like 4,475,619 to 8, something like that. But you're asked here in kilowatts. This answer that you're obtaining is in watts. So you're supposed to convert this now to kilowatts. First divide by 1,000, you're going to obtain 4,447. This was going to change this into a 6 that is now in a kilowatts. So that is the whole idea there of our question. All right, 2 marks for that. And move on to the other part now. We need to calculate the reactive power, which is in kilovolt amperes, kilovars. In this case, that is the kilo as for the reactive power, which is referred to as Q in this case. So our reactive power, Q, so that's 1.34, is given as the square root of 3 times the voltage times the current times the cosine, the sine of theta this time. All right, so do not confuse with the true power in this case. So if you have any confusion, please visit the formula sheet so that you can check how it is given. So in this case, we all have this part. We have got everything. Remember, our VL is not changing. Our VL is still 380. Our line current still 8 amps in this case times the sine of theta. We calculated theta in this case. We got 31.788. So this is the value that you're going to substitute in this case. So this one is going to be 31.788 like this. So with all presentation on your calculator, that is, you are going to obtain 2773.713 like that, which is measured in what? In bars. So that in kilo, we divide by 1,000, that was going to be 2.77. This 7 was going to change this 3 into a 4. All right, that in kilo hours in this case. So that's the whole idea. That's the whole idea there. So we're talking about the reactive volt ampere or the fast in this case. All right, that is how we can be able to calculate this part. All right, so reactive power. Then we move on to the question 2, which was on the conductors, insulators, and cables. 2.1, we are given that an industrial consumer is supplied. All right, so with a voltage of 415 for 3-phase supply. So we're talking about the line voltage in this case here, 3-phase supply. So you're given the line voltage of 415 volts. Then we are asked, determine the maximum permissible voltage drop in any subcircuit of the factory, in any subcircuit. Meaning to say the subcircuit now, we are now talking about the phase voltage affecting there. So meaning to say, in order for us to have, remember the maximum permissible in this case, let us just say we were given a 3-phase supply, that's 2.1. So we have a supply in this case from our 3-phase of 415 volts. So as we know that the maximum permissible voltage we're going to have, we are going to take this one from a voltage drop. It's a voltage drop that you are going to have that is taken from 5%. It's a fixed percentage, which is 5% of the phase voltage, not the line voltage. Of the phase voltage, we are dealing with the phase. So we are supposed to check which connection is it that we have. It's a 3 three-phase supply in this case that we have. So on this three-phase supply that we were given, the voltage being what? 415. So what is going to be the sub-circuits now? Meaning to say here we are supposed to work with what? With the phase. We are going to calculate our phase voltage from the phase that we have here. We need the phase voltage from the line current, the line voltage that we are given. Remember that V phase is equal to VL. We take this as a connection that is happening in a what? In a star connection. Remember our star connection, how it is given. So that is how we take this connection. It's referred to as in a star connection. So that's why we are dividing VL by the square root of 3. So that is going to give us 415 over the square root of 3 in this case, which is going to be something like 239,600 and so on. That's in both. So we have the phase voltage. Like I said, this is referred as in a what? In a star connection. Always, that is what we are going to have in this case. So meaning to say, in order for us to have the voltage drop now, we have the free phase. Remember, to remove the percentage, simply divide by 100. So we multiply to the phase of 239,6 in this case. All right, so that was going to give us 11,98 volts in this case. If it is an approximation, we can just take an approximation of 12 volts there, just an approximation of 12 volts, but that is 11.98. Then from the other part now on 2.2, this one we just need to draw. In this case, we are given to draw a neat label diagram of a PVC insulated wire armored cable in this case. All right, so on the previous, remember on this other paper that we had whereby we're supposed to label this. Now they want us to draw, so please be careful on these questions. All right, so here they are asked to draw. So what we just need is to make sure that we label the parts from the outer sheet, which is the jacket in this case, that, okay, outer sheet in this case that we refer to as the jacket in this case, the armoring, the bending, the insulation, and also the conductors. So like I said, they might give you a diagram like this and ask you to label your diagram. I think we had another question like that, similar. So all you need is to know each and every component that you are given to draw and also to label your diagram. If you can be able to draw this diagram, then it means it mustn't be difficult for you to label it. So know how to draw it. Then the labeling part is then an advantage after. All right, 2.3, give 2 advantages of installing cables according to the open air method. All right, so take note there. We are working with the air method. What are the advantages of using the air method? So the advantages can be it's easier to install, easier to locate or trace a fault. It's cheaper to install. That is the cost-effective part. Easier to repair a fault. Then we've got less labor intense. Cables can be easily replaced. We talk of additional cables can easily be added to same route. Dysfunctional cables can be easily removed in this case. So these are some of the advantages that we can take into consideration. As you can see here, we just needed 2 advantages of these. All right, then the other part on question 3, which was on electrical reticulation. First part was to name 4 sections that make up an electrical reticulation network. What are the sections, the components that makes it up? So in this case, we understand that it starts from the generation, the transmission. So we've got the generation, the transmission, the distribution, and the utilization in this case. So the utilization. So what we need is to understand each of these sections like we are given. They might ask us that way to list or to name any of these sections. The same part is to give 4 advantages of high voltage transmission. In terms of voltages, remember we've got low voltage transmission and the high voltage. So what are the advantages that we have in high transmission? So the first part that we can consider is the use of thinner conductors that are being used. there is a large saving in the conductor material, reduced copper losses, then increased line efficiency. Smaller pylons can be used, and it is almost impossible to steal this electricity. So these are the advantages of high voltage transmission in this case. All right, so just 4 marks for that, which is important for us to know these basics. That is the major part to understand our basics in this case. Question 4.1, we are now given give 3 causes of high voltage surges or of on overhead lines in this case. All right, so we're talking about an overhead lines in this case. What are the causes that we can end up having these surges in this case? So they can be a lot of things, like considering issue for lightning in this case, the on-off switching of large inductive loads. So if we're dealing on that on-off of switching, or the switching of capacitor banks, or it can be from a transient fault. In this case, we can refer to transient faults. So these are some of the faults that we might have, or the reasons, the causes of high voltage surge on overhead lines. Then 4.2, fill in the missing words, all right, in the statement given below. So here we've got a statement that we have that in sense 10142 regulation 6.103 states that fuses that are not installed in a distribution board shall be of the fold of fully shrouded type, or in a suitable, or incorporated in appliance, or incorporated in a switch, or in a. So this is remember, this is like what you need to know this, just like a highway that is the only that you're going to work with as long you are in the field. As long you are in the field, you need to know and to understand each and every part of the regulations that you are given. All right, so the first part that you are supposed to work with the fuses, it must be in a suitable protecting case. In this case, it must be in a suitable protecting case, or incorporated in an appliance, or in a, that will be a socket outlet this time. So this one, it can be in a socket outlet, or incorporated in a switch, or in a, we have got a control gear also. All right, so this part, like I said, these are laws of our electricity. If you're dealing with electricity, we deal with laws. So you have to understand each and every part, like that's your theory, guys. So let us try to revise our theory part as much as we can. Then on the 4.3, name each of the following low voltage circuit breakers. In this case, name each of the following. So from this part, we are given 4.31, that is a maximum operating voltage up to 1000 volts. If the voltage is up to 1000 volts, what is it that we can have? The low voltage circuit breaker. So there we can have a low voltage circuit breaker, or a low tension circuit breaker. So we can use low tension circuit breaker. All right. Then on overload ratings of less than 100 amps, there we can use a miniature circuit breaker in this case. All right. So that is the idea here. We can use a miniature circuit breaker. So this is the same part that we have here, a low tension circuit breaker in this case. That is a low tension circuit breaker. All right, so these are some of the breakers that you might have. So like I said, guys, if you're dealing with theory, just try to revise as much as you can. 4.4, explain the operation of a single phase earth leakage relay under normal healthy circuit operation. What will be the operation of a single phase earth leakage relay? Take note, under what? Normal or healthy circuit operation, when it is on its normal operation or on a healthy operation. All right. So it follows that the current flowing through the live and the neutral conductors are equal in magnitude, but opposite in direction. These two currents will produce magnetic fluxes around each conductor that are equal in magnitude and opposite direction, and therefore the resultant flux around the core region will be zero. So that is when it is operating in its normal or in its health circuit operation in this case. All right, so that's 2 marks for that. Then we move on to the question 5, which is on the application of batteries. Again, we have our theory part there where we are given briefly explain the construction of lead acid batteries. Okay, the construction of lead acid batteries. How are we gonna able to mention this? So lead acid batteries consist of 2 plates, namely the positive and the negative lead. The positive consists of lead oxide and the negative of the sponge metallic lead. These 2 plates are separated using a separator made of the insulating material. The total construction is kept in a hard plastic case, take note, with an electrolyte. The electrolyte is water and the sulfuric acid. So these are the major points that you are supposed not to be missing on our labeling or on our listing in this case. 5.2, give 2 disadvantages of the lithium-ion batteries. What are the advantages in this case? What are the disadvantages, I mean, of this lithium battery in this case? All right, so we have got some of the disadvantages being expensive and so forth. So it needs protective circuitry against overcharge that is sensitive to overcharging. That is, it is too much, and so it need that protective circuitry against overcharge because of what being sensitive. It's expensive. Start degrading as soon as leave the factory. So in terms of degrading, it starts as soon as it leaves the factory. So that is a major disadvantage that we have. It can be ruined if completely discharged. So it means it's not supposed to be completely discharged. Extremely sensitive to high temperatures. Safety contains explodes when overheated. So check what we have, a lot of things. Then transport challenges, limited quantities by air travel. So meaning to say there is a lot of disadvantages that we have there, but we are supposed to just pick any 2. All right, briefly explain why discharged lead acid batteries should not be stored for long periods of time before recharging. Briefly explain why is this, so that after discharging, why is it supposed to be immediately? It must be charged. So it is because of the danger of sulfation. That is, the lead sulfate will form hard crystals that will become difficult to convert back to lead dioxide, and the sponge lead using a normal charger in this case. So that is some of the things that we are supposed to consider, which can be a disadvantage if we're to list the disadvantages of a lead acid in this case. But we explained the construction of lead acid before. All right, so 5.4, a lithium ion battery is made up of a number of cells, and each cell is made up of 4 components, namely the cathode, the anode, the electrolyte, and the separator. State what the separator is made up of. We are not even talking about the cathode, anode, no, the separator. What is it that is made up of the separator in this case? All right, so our separator is simply made of the synthetic resins such as polyethylene or propylene in this case. That is the other part, that is the polypropane. That is the one that we have, or we have got polyethylene in this case, ethylene in this case from our member. We've got those ethylene and also the propylene which is polypropane in this case. All right, so that's what we are going to have on our lithium ion battery, which is another part of our battery in this case. So this it's a lot of theory here. All right, 6.1, we are asked to draw. All right, let's see what we have on 6.1. We are asked to draw a neat labeled circuit diagram of a manual faceplate starter used to start a series motor. All right, so that's we need a diagram in this case. If we check, I've got something here that we can consider, whereby we have got our supply and having our capacitor here, C1, and the series resistor, the armature. We've got armature winding in this case, then the spring loaded starting arm and so forth. So that is what we can have. And we can actually have this diagram in another way. I just hope I did not, but I didn't put it here. So I just hope I'll have it on another part. I had another diagram again, similar to this one. Then now we are asked to list 3 components of the armature assembly of a DC machine. What is it that we have on a DC machine in terms of its armature assembly? So it is having the armature core, the armature windings, the commutator, the shaft, the bearings, the cooling fan, and also you need to list the armature conductor. For this one, you also have to mention the armature conductor. All right, so that is another part that is important to know. As you can see, 10 marks from this part, which is fine. All right, then we are given on the other part of our question, which is on the AC machines. In this case, dealing with our AC machines. 7.1, complete the following table regarding the testing of 3-phase induction motors by writing only the answer next to the question number from this part that we have name of the test. Then we are given the instrument used, the minimum allowable reading from this one. All right, so 7.11, we are given insulation resistance test between windings. What is going to be the instrument to be used? So there we can use a mega tester. In this case, we can have a mega or an insulation resistance tester. We can use that as an insulation resistance tester. Then the minimum allowable reading for this is supposed to be 1 mega ohm. So that is the minimum requirement, 1 mega ohm. Then for earth continuity test, we are going to work with the multimeter. That's the best that we're going to work with, the multimeter in this case, or a mega test, or on the ohm scale, on the ohm scale, because we need to have like resistance for that. So we are going to put our mega test on the ohm scale. So there we are already given in ohms the minimum values 0.5 and so forth. Then the insulation resistance test between the windings. All right, the insulation resistance test between windings and earth. Again, there we can apply this mega. In this case, we can apply our mega test in this case, or the insulation resistance tester. Again, for insulation resistance. All right, so this one is just a repeat. Here we just said insulation resistance test. I'm wondering why am I having a repetition? All right, so this one is between now the windings and the earth, which is the same as what we have there. So even the resistance there, 1 mega ohm is allowable as a minimum requirement. All right, list 3 characteristics of AC series motor. What is it that we consider on an AC series motor? These are the characteristics now. So you can talk about the high starting and operating torque in this case. All right, so let me show you some of things that you can consider. So like I was saying, we can consider the part of the high starting and operating torque in this case. Whenever you're starting this, torque of variable speed, dangerously high no load speeds in this case. So these are some of the things that you can consider as the characteristics of an AC series motor. All right, on question number 8, which is on transformers, we are given the first part. It was to draw a neat labeled vector diagram of a transformer on at no load. Take note, this is at no load because it can be on load, and here we are asked to have this one working at no load in this case. All right, so this is what you're going to have. You must be able to state, to mention all the currents, the no load current, magnetizing, and the component. In this case, all the components that you're given and the angle. Remember, this angle will be taken to this point here. This is the same angle that you see here, the same angle that you're going to apply here. That is why you see now applying this side from our IO sine of theta, IO cos of theta. So the part that we are having is from the angle that we have in this case from our diagram. It's another part that we are supposed to actually work with on separate part, like try to consider this diagram and the other one entry calculation. So we shall see that with time. So we'll try to separate this class. In fact, to separate a class on transformers, that is what we are going to do. State the functions of the magnetizing and core loss components of the no load current in this case. So I asked to state, meaning to say we just need them, the functions in this case. All right, so we're given that the major function of the magnetizing component is to produce the magnetic flux, while the function of the core loss component is to supply the iron loss as well as the small copper loss occurring in the primary windings. All right, so with this part, you were going to obtain all the marks. 8.3, a three-phase distribution transformer has a star-connected primary. All right, here we want to be very, very careful here of the information. We have to be very, very careful. We are talking about a three-phase distribution transformer. It's a transformer, yes. But on the primary, we've got a star connected. On the delta, we've got a secondary connected. All right, so let us just have this aside. This one is interesting. This one is an interesting question. All right, so that's 8.3. So like I'm saying, this we have got the primary on this side, then we have got the secondary. All right, so on the primary, this is happening. It is star connected. All right, so it is star connected, whereby we talked about the formulas as we saw from our formula sheet, that in a star connection, the line current is equal to the phase current, but the voltage now is equal to the square root of 3 of the phase. Then the secondary part, we are being told that this one is in a delta. All right, so we also talked about this, that in a delta, we are going to have now the voltage, the line voltage equal to the phase voltage, and the line current equal now to the square root of 3. So the line current is equal to square root of 3 times the line, the phase current in this case. We talked about this also on our information sheet. From our information sheet, we said this is given. This information is given in our information sheet, as I showed you guys. So that was the connection that we have. We shall see now later on to say what is it now that is happening. And we are given that the secondary is delta connected. All right, the transformer is supplied at, meaning to say we are talking about the voltage that is in the primary. And this voltage that is supplying in the primary, we are talking about the line voltage in this case. And the secondary voltage, the secondary phase, they are telling us this one on the secondary, it's a phase voltage. All right, so let's start with the primary. The supply is on the primary. All right, the supply is on the primary, and this supply is taken, we are having this as our line voltage. So here we have got our line voltage in this case, which is given as 4,4 kilovolt. That's 4,400. something like that, 4,400. If you multiply times 10 to the exponent of 3, you're going to have 4,400 volts. And on the secondary side, we are not given the line voltage. We are given the secondary phase. It's a phase voltage. So there we have got a phase voltage on our secondary. We are given the phase voltage of 254 volts in this case. So that's the information that we are given. And the question is, from this part that we have, calculate the turns ratio of the transformer. So you need the turns ratio of the transformer. Knowing that from our part, if we are to talk about the turns ratio, that is N1 over N2. All right, so we're supposed to have this as N1 over N2, the number of turns on the primary to the secondary. So here we're talking about the primary that you can refer as 1, secondary as 2. So we are supposed to be working with this as N1 over N2 is equal to the voltage, but this voltage is supposed to be the phase voltage to the phase voltage of the secondary. Or we talk of the current, that is the phase current of the secondary to the phase current of the what? Of the primary. Take note, we are working with the phase. Already on the secondary here, if we had to take, we do not, both primary and secondary, we are not given the number of turns, but we are given the voltages. But already on the secondary, we are having this voltage in phase. That's a phase voltage in this case. So this is the secondary side. So you can just write a 2 to show that we are talking about the secondary side. We already have the phase voltage on the secondary. So meaning to say, we can consider this formula to say, instead of using N1 over N2, we are simply going to use VP1 over VP2. That is the phase voltage of the primary to the phase of the secondary. But on the primary, we do not have the phase voltage in this case. If we check on our primary, we have the line voltage on this part here, VL. That is our line voltage. And this is in a star, it is star connected, all right? So let me just even write it here, it can be fine. This is in a star. So meaning to say in a star now, we are supposed to work with this formula in order for us to determine our phase voltage in this case, where we said in this case to find phase voltage, just divide by the square root of 3. So that means the phase voltage is going to be the line voltage over the square root of 3. So that's the phase voltage is the line voltage. We have our line voltage in this case 4,400 or 4,4 times 10 to the exponent of 3, which is same as 4,400 over the square root of 3. So this is going to give us the phase voltage in this case for the primary, which is going to be something like 254 0,341, something like that, 341 in volts. All right, so this is from the primary. So we're just going to write SVP1. So thus with this information, we can be able to find our turns ratio, because we are saying our turns ratio can be taken from this formula, from whatever formula that we are going to have in this case. So since it was supposed to be N1 over N2, as we are going to use the VP1 over the VP2, the phase voltage, well, that's what we have. We have the phase voltage in this case. All right, so we've got the turns ratio is going to be on the primary, our voltage from the phase is 2,540,341. Then on the secondary, our phase voltage is already given as a 254 in this case. So that was going to be 10,000 and so forth. This is what you're going to have. So meaning to say it was supposed to be 10, like 10 over this number. So it simply means we have got 10 over 1 in this case, 10 over 1, which means we can simply write this as 10 as to 1 as our turns ratio in this case, 10 as to 1 or 10 over 1. We simply say N1 over N2 is 10 over 1. That's the relationship between N1 and N2. And also it can affect even for the voltage, as we even took this from the voltage. So that was the idea of our question. All right, now let's see this part here. This is the major part here that they are saying. The primary current, if the transformer delivers a line current of 145, if it delivers the transformer is delivered, that is the output. We're talking about the secondary current there. But this secondary current that we are given, it delivers a line, it's a line current that we have. So we need to calculate the line current of the transformer. The primary line current is the one that we are supposed to calculate. All right, so let's just have it here. We are supposed to calculate the line current here of the primary. That is our question. All right, so on the primary, let's see if it is 8.32. On the primary side, we are supposed to calculate the line current in this case. This is the one that we are supposed to have. All right, let's just write the same way that I used here, P1, and so that I do not confuse you guys. All right, so I'm just going to write is 1, L1, 1 for the primary, but you can write this as P. And for primary, you can just write P, all right? But same part is just using a 1. So this is the one that you're supposed to calculate the line current, whereby we know that in a star, the line current is equal to the phase current, because we have told that on the primary, it's a star connected. So we shall talk about this depending, because what we are going to use from our formula, this formula we're going to work with what? With the phase. So let us check now what we have. We are given the line current of the secondary. It delivers this current, which means that is what we have on the secondary side. And on the secondary side, we are dealing with a delta. In this case, this is what we have. All right, let's see. On the secondary side, we are given our line current as 145 amps. This is on the secondary. And on the secondary, our part or the transformer is in delta. And we know that in delta, the line current is equal to the square root of 3 of the phase current. So that means we are supposed to calculate the phase current. Why calculating the phase current? Because here on this formula, these values should be in phase, like I explained before. They must be in phase. So meaning to say, we are going to calculate the phase current from which formula? From the formula of line current equal to square root of 3. So in this case, we are going to calculate first the phase current for the what? For the secondary in this case. So the phase current here is simply going to be the line current divided to the square root of 3. So that means here we are simply going to divide. That's the phase current for the secondary is going to be the line current on the secondary over the square root of 3, of which the line current there is 145 divided to the square root of 3. We are going to have the phase current in this case, which is going to be 83,716, something like that, 83,7158 and so forth. So it's going to be 716 in amps. All right, guys, do not confuse here. The question is, we are supposed to calculate the line current of the primary in this case. On the primary, it's not a big deal, because already we're dealing with a star connection whereby the phase current is the same as the line current. So meaning to say, we are simply going to calculate that phase current from where? From the voltage, from the turns ratio, this part that we have about our currents. Remember, from our turns ratio, we are saying 10/1, this 10/1, it's N1 over N2. So we are given that N1 over N2 is equal to, that is the 10/1, the 10^1. This is equal to, when we are talking about current now, take note, it's now IP on top. Meaning to say, we are going to use this formula in this case, whereby we are saying the second one on the secondary side, that is this one on the secondary side, in phase, not as the line current. That is why we have to change this line current to a phase, because these values are supposed to be in phase. So we are going to have the value of 83,716 over the current from the phase. From where? From the primary, which is the one that we are supposed to calculate in this case. By finding this current from the primary, we are calculating the current in the secondary. So this one, we do not have the phase current of the what? Of the primary. So that was our question. we play around with this. We calculate the value of what? We calculate the value of this current, cross multiply here. That's going to be 10 times the first current in the primary is equal to 83,716. Divide by 10 both sides. Since we are multiplying here by 10, we are going to divide by 10 both sides. So we are going to obtain our first current as that was going to give us 8,3716, which is going to be a 2 in this case in amps. But remember, in the primary, what we said, in the primary, we are dealing with what? A star connection in our primary, whereby the line current is equal to the first current. And as we're being asked to calculate the line current in this case, so therefore, our line current is equal to this phase voltage. So therefore, our line current from the primary is going to be equal to 8,372 amps. Take note, our question is to calculate the line current, but we are dealing with a star connection where we know that these two are the same, the line current and the what? The phase current. So as you can see, it was a nice question to play around before you attempt exams. This is a nice question to understand. It gives us a lot of information was hidden there, but it's actually fine. Let us check the question number 9 there, where we are given on earthing. All right, so we are now on earthing. 9.1, we are given explain how overhead lines are earthed. So that is the earthing part, but we are dealing with what? An overhead. An overhead is the one that we are dealing with. So on an overhead, in terms of earthing, the earth continuity conductors are erected above overhead lines to protect them from lightning, and it is also useful for earthing pylons in this case. So that is the part that we are given on them on the overhead. How are they being earthed in this case? 9.2, show by means of a block diagram how leakage current from any part of the insulation is directed to the ground. Take note, how is the leakage current directed to the ground? So it's actually a flow, just like a flow chart. This is what we have, how it is directed. So we've got the earth fault, the leakage current, to the earth continuity conductor, to the consumer's earth terminal, to the earthing conductor, the supplier's protective conductor, to the earth electrode buried in what? In the ground. So these are the stages or the flow chart of how it is supposed to be like in this case. So that was actually 6 marks, the block diagram, just like a flow chart that we have, and it's just supposed to indicate everything for you to obtain all marks, which is the 6 marks there. 9.2, explain the concept of the part of touch voltage. How is it applied in this case? That is the touch voltage. So this is simply taken from the shock hazard concept. All right, so let me have it this way. The way that I'm from this one, the shock hazard present on any exposed metalwork or protective conductor in this case, which can be the touch voltage, which is can be appeared from the simultaneous accessibility, all right, which is from being accessible of the conductive parts in this case during an insulation part. So that is how you refer to a touch voltage in this case. So that's it. We just need our theory there, our theory, guys, our theory. Like I always say this, that's why I refer to as electrical trade theory. We need to understand our theories much. All right, I want this back here. All right, sorry for that. So let us check the other part. We are given on the measuring instruments now, this part of measuring instruments now, have said a lot about this, so we're not going to waste much time here. Question 10, 10.1, a moving coil instrument is an internal resistance of, all right, let's check what we have there. Still have, all right, almost done. Almost done, almost done. All right, so let us check here what we have. We have a moving coil instrument. Remember, it has an internal resistance of this and gives a full-scale deflection. I said whenever you're dealing with this condition, we want you to check on measuring instruments, to check on the industrial electronics N2 videos, so that you check. I've explained there on the measuring instruments questions. So just try to grasp a lot from there. All right. So what you simply need is that on a measuring instrument, you have the meter. In this case, this is going to be our meter. At full scale deflection, this meter, it has its own limitations or characteristics that it possesses, like the internal resistance of this meter that we see here. We have its internal resistance, that is the resistance of the meter, given as 100 ohms. And at the full scale deflection, it's going to give us a current of 5 milliamps. We also have the current across the meter, which is 5 milliamps. So this is our meter in this case, or the scale, the instrument. But on this instrument, there are adjustments that are being made now, whereby they are saying determine the value of an additional resistor needed to convert the instrument. Take note, we can either convert this to measure voltage or to measure current. So here they are saying it is to convert the instrument into a voltmeter within a range, with a range of 0 to 15 volts, meaning to say now it can measure up to 15 volts. Take note, this one we are going to have an additional resistor to this part in series, that is for us to measure a voltage up to the value that we are given there. So we are going to add a voltage in series like this. So that is the condition of our question. So we need to know this resistor that is going to allow this instrument now to measure a voltage across from 0 to 15, meaning to say at its maximum, it must be at 15 volts in this case. So that is the question. That is the whole idea of the information that you are given there. So this is the series resistor in this case. This one is our series resistor. So as we know that here we are going to have a voltage drop across the series resistor, and we also have the voltage drop across the meter. So as we are asked to calculate the resistance across the meter across this part here, which is this resistance, that is the one that you're supposed to calculate. Determine the value of the additional resistor. So what is the value of RS in this case? All right. So on your measuring instruments here, without wasting much time, you're going to check that I listed some of the other things that you can see here. We are also given that for a shunt resistor, this is what we have. But for a series resistor, which is the one that we are dealing with, we can calculate that by V over IM minus RM. That is the idea there. So we can have this formula as in consideration, guys. We can simply have this formula. So meaning to say that's the formula that you're going to take into consideration, or you can make this the subject of the formula. There are a lot of things that you can consider there, but here, because of our time, let's just consider our formula. So you're saying RSE is going to be V, that is going to be V over IM minus RM in this case. All right, so that is what we are being given from our formula. So that means we can calculate our RSE, which is the series resistor, V, which is the supply voltage of 15, over IM, the current across the meter at full scale deflection. That's 5 milliamps, 5 times 10 to the exponent of minus 3, minus RM, which is the resistor, the resistance of the meter, the one that is taken across the meter. All right, so from this formula, we can be able to calculate our series resistor, which is going to be something like 2,900. So we're going to have 2,900 ohms, which is in kilo ohms. That's 2.9 kilo ohms in this case. All right, so that is how we can have this at the end. All right, 3 marks for that, 3 marks for that. As you can see, you can use the formula direct, but just for the purpose of revising, also you need to understand what is it that we are talking about there. But as you can see that the formula is there, you can use our formula direct. In any circuit operating on question 10.2, we are given that at high voltage or high current, the measuring instruments are indirectly connected. State how each of the following meters are connected in such circuits. If we are dealing with a meter in any of the operating circuits, how are these meters connected? That is the question. All right, so the first part that we are given is an ammeter. So for an ammeter, what we are going to see is that the connection there is going to be connected to the secondary side of a current transformer. So this one is connected to the secondary side of a current transformer. All right, if we check the other part, it was for the current coil. In this case is connected. That is, in this case, we are moving to the watt meter. All right, on 10.22, that was for the watt meter in this case. All right, we are dealing with the watt meter. The current coil is connected to the current transformer, and the voltage coil to the low voltage side of the potential transformer in this case. All right, then the last one was on the frequency meter, and on the frequency meter, this is what we have it connected to the secondary side of the potential transformer. This is for the frequency, what for the frequency meter in this case. So I just mentioned all of them at once. That is the idea of our question in that case. We talked about all of these. Question 11 on renewable energy. We were now given briefly explain how the following renewable energy sources are used to produce electricity. How are we going to use biomass in this case to produce electricity? It's actually another part that is important on the production of electricity. So for biomass, what we need is that is burned in a furnace, and the heat energy is used to produce steam to drive the steam turbine in this case. That's how we work with what with the biomass in this case. It is in a furnace that is just to, and the heat energy there is the one that is used to produce what steam. What we need there is the heat energy that is going to produce steam to drive the steam turbine. Once the steam turbine is rotating, then we've got the generation of what? Of electricity there. Then the last one is the geothermal electricity. How are we going to end up with a geothermal electricity? What is it that is affecting? So it's from the geothermal energy. In this case, we are saying the geothermal energy is the heat that comes from the rocks and fluids found beneath the earth crust. This heat energy is used to produce steam that to drive the steam turbine. As long we have the heat energy, we are now having the production of steam, which is going to drive our steam turbine, which is the same thing that we had on our biomass in this case. It is burnt in a furnace. When the heat is being released, that heat is the one that is going to produce is used to produce the steam, and that steam now drives the turbine. Once the turbine are rotating, then we've got the generation of what? We have got the generation of electricity. That means we now have electricity at the end. So that is what we just needed in this platform from this paper. That is what we needed to. So you just need to revise, especially our theory. Come back for your calculations, revise your calculations. Some of these calculations, we've explained them from our industrial electronics there. So you can just check some of these calculations in the theory part. For the theory part, you just also revise along so that if we explain, then it makes sense, because some of these things it will be like, why there's no such explanation? Some of it I'll be seeing like it's direct and so forth. So can we revise on our theory so that if we have a part that is having a challenge or a part that we are not understanding, we can come back with it so that we can work that part together. But for now, that's it, guys, from us on African Motives. Till meet again.